So today we're going to be solving the problem that happens when our character controller runs down slopes. So as you can see, as my character controller starts running down the slopes, he sort of hops down it instead of actually running down the slope. And so we're basically going to be using a completely new object called ground direction that's going to examine the floor below us and point our character in the right direction and make sure that our character is actually maintaining speed with our forward direction. So let's begin. First couple changes I'm going to make. I'm going to come up to the slope limit and put in 55 because I think that's close to what the slopes of World of Warcraft are. They're probably more extreme. I know you can climb up some pretty crazy slopes, but yeah, it's going to be 55 for the time being. And then I'm going to create a new empty. We're going to call this one ground direction. This is what we're going to use to tell the controller which direction the ground is facing. Alright, so now inside our script, let's come down to component references. I'm just going to change that to references. And under character controller, I'm just going to put up public transform. We're going to call this one ground direction. Then I'm going to click on the player and drag ground direction into there. So now I'm going to grab a model that I've created in Blender, and that's this model. It's a very, very simple just axes. I'm just going to take the axes blend and drag it right into here. Cool. And so now I have the axes. And I'm just going to take the axes, drop it into ground direction, and I'll just very quickly switch it so that there's no extra information that I don't need. Like the animation, there's no animations on this, so I don't need any animations. So we've just got the model and the materials. Alright, so now it's super tiny, and it's also not in the right orientation. So I'm just going to go reset transforms, and then I'm going to scale it up by 10 on all of the axes. Cool. But now I kind of want to see it, so I'm going to take the player, I'm going to change the rendering mode to transparent, and bring down the alpha of the color. So now we can see our axes. Now we're going to come down to before jumping, and I'm going to go void ground direction. And I'm just going to take this ground direction and put it right at the beginning of locomotion because I want this to run every single time we're doing locomotion right at the beginning. And then underneath running, I'm going to create a new ground category. And I'm going to create a couple variables. So the first one is vector3 forward direction. Second one is going to be float slope angle. And then underneath that I'm going to create a new ray. I'll call this one ground ray. And a ray cast hit called ground hit. Alright, so now inside here, first let's take our forward direction and we're going to set it equal to transform.position if input normalized.magnitude is greater than 0. Then we want to set forward direction plus equal to transform.forward times input normalized.y plus transform.right times input normalized.x. And then we're basically going to go else forward direction plus equals transform.forward. So essentially, I'm basically creating a normal from the position of the player controller, and then creating a normal essentially pointing in the forward direction based upon our movement. After that, we're going to set the ground direction by doing a ground direction is a transform, so it's going to be a look at. It is a transform, correct? No, that's not right. Ground direction, there we go. Dot look at, nope. Dot look at. And then we're just going to look at forward direction. So let's see that in action. So now, as you can see, it's essentially pointing in the direction that we're moving in. And since we're going to be using this to dictate our movement direction when we go down hills, one thing we might as well update and change is this here. Because essentially what we're doing is we're just plugging this entire thing in up here. So we may as well just take ground direction forward and multiply it by input normalized dot magnitude, and then multiply that by current speed. So essentially all of the same stuff is happening, except now it's happening as a result of the ground direction. Alright, so let's just quickly comment that. So setting forward direction to controller position. Let's make that all one word. And then setting forward direction based on controller input. Based on control input. And then setting ground direction to look in the forward direction. Normal. Alright, so next let's set up our rays. Our single ray, actually. There's only one. And it's going to be ground ray dot origin is going to be equal to transform position plus vector 3 dot up times 0.05f, and then ground ray dot direction is going to be equal to vector 3 dot down. Cool. So now that we've done that, we can create our if statement, essentially checking to see if it's colliding. And we're going to put in physics.raycast, and we're going to put in our ground ray. Then we're going to put out hit, nope, not out hit, ground hit. Then we're going to put a distance, and that's going to be 0.55f. Not origin. Did I type in O instead of 0? Silly me. So the first thing we're going to do is we're going to get our slope angle. And essentially, our slope angle is going to be equal to vector3 dot angle, and that's going to be vector3 dot up to ground hit dot normal. So if I just go into the script and write above slope angle, put serialized field so that we can see what we're doing, then when I press play, we should have our angle. So our current slope angle is 0, right? And then as soon as we start walking up, you can see that that's the angle of the slope. But the problem is, we kind of want to get the angle of the slope based on the forward direction, because we don't want to apply our movement changes when we're moving up the hill, right? And the angle based on the forward direction is going to be, I guess, in the positive direction, and then if we're going down the hill, it's going to be in the negative direction. So what we're actually going to need is we're going to need another angle here, and we're going to call this one forward angle. And we're going to calculate forward angle here based on vector3 dot angle, and we're going to use forward direction and ground hit. Oh, I think I misspelled ground hit. One second, let me change that real quick. N. Let's just see where the errors pop up. So here's one, here's another, here's another. Cool. And actually, I'm just going to change this to transform up, and maybe instead of forward direction, we'll just go by ground direction dot forward. It's pretty much the same thing, but okay. So now when we look at it, what does it look like? Alright, so here we go. So here's the first major issue, is it's basing it off the fact that our forward angle, so essentially, if we look at our character, the normal of the ground that our character is standing on is directly up. And since we're taking the forward angle, obviously that angle is going to be 90 degrees. So what we need to do is we need to subtract 90 degrees from this. So I'm just going to come right here in the end, not minus 90, and that should give us the angle that we want to see. So now it's 0, and once we get on the hill, it's positive, and then when we turn around, it's negative. Cool. But here's the thing, right? In order to make the proper change to our normal direction, we essentially need to change our ground direction. So first, let's just grab, no, let's not grab all this yet. Let's create a new if statement inside our raycast. And let's go if forward angle, nope, not forward direction, forward angle is less than 0. And then we're going to go ground direction dot Euler angles. I made a mistake of mispronouncing that last time I said it. Euler angles is how I pronounce it. It's pronounced Euler angles. Not a huge issue. Then we're going to go plus equal new vector 3, and we'll put in forward angle 0 and 0 just for now. And let's see how that does. So currently we're moving up the hill, so nothing's happening. And now we're moving down the hill, and as you can see, it's pointing in the wrong direction. So I think what I have to do is I have to put a negative in front of it. And I'm just going to reset the player position. So now what we have works, right? And it works regardless of the direction that we're moving in. So yeah, as you can see, since we've changed the rotation, when we move down the hill, it is a much smoother movement. So note that I actually changed that on the x-axis, and that's because that's the axis that I wanted it to rotate around. So let's just getting angles down here, setting movement direction. Let's just say setting ground direction based on forward angle. Okay, so in order to demonstrate one of the major problems that this creates, I'm actually just going to have to make a few changes here. So first, I'm going to take this guy and I'm going to, let's use faces. I'm going to raise this, like right there. Grab this, grab this, pull it way back. That should be good. And then I'm going to go back to edge select mode. And what I'm going to do is I'm going to grab these two edges, go to subdivide edges to where it says plus, and then under subdivisions I'm going to hit 2, put 2, and then press the button. And that'll subdivide it twice. But you can't see any edges, but if you actually mouse over the new edges that you created, you can see that they're there. And essentially the problem is it creates the new edges, but it doesn't actually connect them. So I'm going to have to connect those. So I'm going to select this one first, hold shift, select the next one, and click connect. And then I'm going to do the same thing for here, connect, and then just kind of round everything out. Just going to connect one more, and I'm not going to connect the other one because I'm going to modify this. I'm going to move it up first, and then I'm going to move it forward, maybe move it downwards a little bit. So I think probably this is good for now. Should be good, yeah. And then we have a quad here, and we can make this one a quad. So just merge faces. But honestly, you don't have to do that if you don't want to. It's just extra work that I'm doing. Cool. So now, let's take these two walls. Let's bring them back up. And I'm just gonna pull it out over here. Pull it all the way up. Same thing on this side. Pull it out over here. Pull it all the way up. And that actually should be good for now. Got a pretty bright spot in the corner over here, which is a bit strange. So maybe that's just some vertex colors that need to be, yeah, there we go. Alright. So now, let's have a look at what's going on. Alright, so we're going to try and run up this. Yep, it works. And then if we turn around and run down, it seems to work, except when we get to here, we run down that hill extremely slow. So we run up it really fast, and then we run down it really slow. And so we essentially need to create a multiplier that ensures that when we run down the hill, it's actually at the same speed that we run up the hill at. So let's go to the top here. Let's go right below slope angle and forward angle. We're just going to go float. We're going to call this one slope mult. Probably hide these. We don't need to see them anymore. And basically, in order to get the number, it's a bit of trigonometry. So, alright, so to demonstrate how we're actually going to solve this problem, let me just draw it out. So here we have our hill, and we have our player, and our player moves forward in this direction. Now what we've actually done is this, we've taken this forward direction and we've rotated it onto the ground, right? Now, I'm just going to blow this up a little bit so that you can see a little better what's going on. So this is our player's forward direction. And when we rotate it like this. But what this means is that even though this distance is probably like the same length, what's actually happening is our horizontal speed is now right here, which is like 2/3 of the speed. So now we're going at a much slower speed. But if you actually look at this, like this is a right angle triangle here. So essentially, all we would really need to do in order to figure out how to make sure our speed matches our horizontal speed is to create a right angle triangle from the max speed and then find out what this is. So what we have here is this is our player's origin. So this is we'll call this this is our speed. This is the angle to the ground. I'm just going to call it theta because it's very simple to remember. And this is going to be our speed mult. So this is going to be S, SM, and this one, I guess we'll just call it OP for opposite. Because if you remember in trigonometry, this is the adjacent angle, this is the opposite angle, and this is the hypotenuse. So basically what we have to do, we have to figure out using trigonometry what the speed multiplier is. Essentially what that means is we're going to have to use there should be an H there, ka toa. So let's very quickly figure this out. So we don't know what the speed multiplier is. We don't know what the opposite is. We know what the theta is, and I'm not going to actually give a number here, but we also know what the speed is, which is 1. Let's first, if we look at it's a sine theta is equal to opposite over hypotenuse. So since we don't know either of these numbers, this is out. And then cosine theta is equal to adjacent, which is 1, over hypotenuse, which is SM. And then TOA is tan theta, which is equal to opposite over 1. So it seems like these two are the only two options. So from there, let's figure this out. So cosine theta is equal to 1 over SM. And essentially, what we can do here is we can cross multiply and divide. So if we just do that, then essentially it's just going to be cos theta times SM is equal to 1 times 1, which is basically just 1. And then what we can do is we can divide cosine theta on both sides. And what we end up with is SM is equal to 1 over cosine theta. And that's pretty simple. That's something that we can figure out. So I feel like this is a prime candidate for what we want to do, right? So now that we know that, let's also try tangent. So very simply, tan theta is equal to opposite over 1. That should not look like a 4. That's close enough. Alright, so now very simply 1, we can just cancel that out because it's basically just opposite over opposite, so it's just 1. So tan theta is equal to opposite. And once we have opposite, what we can essentially do is we can take opposite and speed. So opposite squared plus 1 squared is equal to SM squared. And then from there, just take this, and I mean we can square root it. So SM is equal to the square root of OP squared plus 1 squared. But essentially what you have to do is you have to do this. You have to do this first. And then you have to do this. And so I think that the best option is this one because this is just much simpler to do. Alright, so let's start setting that up. So if you remember, what I did was I broke down the options that we have, and we can use a tangent or we can use the cosine, but I'm going to use the cosine. So first, let's take it's a slope mult, and I'm actually going to change that to forward mult for just so that it's easier to understand what it is. So forward mult is equal to 1 divided by mathf dot cosine, and then theta is the angle, which is the forward angle. And since this angle is in degrees, we actually have to convert it to radians. So mathf dot deg to rad. That's basically it as far as I understand it. So I'm just going to serialize this, then take it, forward mult, and apply it to our current speed inside some brackets. Multiply, forward mult. Okay. Now let's have a look and see how this is functioning. So there we have our forward mult. Let's see what this looks like. Oh. Okay, ran into our first problem. Essentially, when the forward mult isn't on any kind of an angle, it needs to be set to 1. So here, we're just going to set it equal to 1, and that's all we need to do, so it's just always going to be set to 1, regardless, until we hit an angle, that is. And that way we can make sure that we are able to move. Okay, let's do this. So, standing on this angle, and as we turn around, perfect. So we get a multiplier based on the angle that makes sense. And it speeds up our character exactly as much as we need it to. Cool. Now, there's actually one other issue that needs to be solved here, and that's right at the end there. You can see that it's resetting the ground direction way before we actually touch the flat ground, and we need to solve that. So I basically want to make sure that whenever I'm touching a slope, the direction is following the slope. And in order to do that, I need to create a new vector 3, which I'm going to call collision point. And then down here, I'm going to go void on collider. No, that's not right. On controller collider hit. And I'm just going to go collision point is equal to hit dot point. And that's going to make sure that collision point is being stored from wherever the collider is hitting. But we actually need to bring that up here where we're setting up the ray's origin specifically, to change transform position to collision point. And now what should happen is it doesn't matter really, as long as, yeah, there it is. It's just a much smoother transition now. And it's the same thing for those angles, even though those angles were never really that much of an issue. Alright, I hope you enjoyed that. Recording this episode was substantially easier than last time, except I just didn't have a lot of time to do it because I'm back to work. So I'm going to be trying to keep a weekly update schedule, even though I completely missed that date with this video. And in addition to that, I might try doing some other smaller projects just between episodes to give myself a little bit more time to work on these if I need to. But yeah, I don't know. Let me know what you think down in the comments. And thanks for watching.
Super trooper, super trooper, super trooper, and he sells soup.